In this session, I want to demonstrate what we worked on last year regarding the drawing optimization tool suite, which can be found in the Manage tab over here. Drawing optimization tools have been there since last year, and we started this development because we believe that BricsCAD can help you to display, store, and to use your data in the most optimal form. It is very easy to create a file that contains a lot of data, taking up a large portion of your disk space spanning multiple megabytes or gigabytes, which is structured in a bad way. But it is very hard to restructure this file and to reduce its size again. As such, we started working on a broad range of intelligent and automatic tools which help you organizing and optimizing your files. These intelligent tools automate tasks which would otherwise take a lot of time and manual work. Today, I'm going to talk about some of these tools which have been improved over the last release cycle. One of these tools is Optimize, which was introduced last year, and the goal of this tool is to analyze the geometry in the drawing and to search for places where it can be optimized. This can mean, for example, to close the gaps between these lines or to rectify any skewed lines. This year we have extended the functionality to other supported optimizations. For instance, we have introduced the possibility to optimize polylines and arcs. If we go back to this example again and launch Optimize, you see that we have replaced the previous dialog with a command panel. And this command panel will remain active during the lifetime of the command and will automatically close when the command finishes. You can see that the lines that will be optimized are being highlighted, and if we, for instance, change the angle tolerance to a lower value, you can see that less lines are being highlighted, which also means that they will also not be optimized. Let's put it back to 2. We have included a preview option. If you press preview, you can see what the command will do. But you also can see that, for instance, over here, the settings are not sufficient to close this gap. So if we go back and also exit the command, so we can measure the gap distance. See, we have a gap distance of 0.35. Launching the command again, we will increase this gap tolerance to 1 millimeter to have sufficient margin over the 0.35. You can press preview again, and now we can see that this gap is also closed and these entities are all nicely optimized. We can also go to the Polyline and press preview to see what these settings will do, and they are not sufficient to optimize this structure. So we will increase the angle tolerance to, for instance, 4, press preview again, and now these are nicely optimized. Also go, for instance, to this arc here, you press preview. Here you see that on the right, this gap is being closed, but this gap is not closed yet. In order to close this one, we'll increase the gap tolerance to 3 millimeter. Press preview again, and now we can see that all the gaps are closed. If you're happy with the result, you can press OK to finalize the command and to execute the optimization. You can also see over here that not all gaps can be closed, because in this case there's no intersection point between the arc and the line. If we have a look at a more realistic example of, for instance, this floor pan here, we can see that there is a lot of room for optimization. For instance, here you can see a lot of skewed lines. You can also see over here a gap of around 8.9. You can also see over here a gap of around 5. You can see here we have some skewed lines. So there's a lot to improve. Launching Optimize and looking at what we measured for the gap, we can fill in, for instance, a gap tolerance of 10 and launch Preview. You can see it's already improving quite a lot, but also you can see that this line is still not being optimized. If you reset the preview, we can see also that this line is also not selected. So we have to increase the angle tolerance until we see that it is selected. around 6.8. It is selected, so let's put it on 7. Press preview again. And now we can see that this is also being optimized. If you are happy with the result, you can press OK to finalize the command. In BricsCAD V22, we have extended the optimize command to also include 3D geometries. For instance, in this simple 3D drawing, we want to align this top face to these top faces. And let's first have a look at the slope of this face, which is 173.2. And we also want to align these faces to each other. So if we launch the optimize command, you can immediately see that the optimize command has recognized these two faces to be optimized, but it still didn't highlight this top face. In order to do that, we will increase this angle tolerance to 7 to make it 180 degrees. And we can press preview to see the results. We see that this one has been optimized, but here we have still a distance between this top plane and this top plane. If we reset, we can increase, for instance, the distance tolerance to 300 millimeter. But now we can see that the optimize command has included also other faces to be optimized. And if we press preview, we can see that all these gaps are being closed, which is not what we want. In order to solve this, we will put the distance tolerance back to 100 millimeters and apply it for a first step. And in the next step, we will align this top face to these top faces. In order to do that, we'll increase the distance tolerance to 300 millimeter again. But now we will disable the YZ plane and the XZ plane optimization, and only this top plane is now selected. We can press preview to make sure that it optimizes what we want. And if we are happy, we can press OK to finalize the command. Optimize in 3D can do much more. For instance, here in this more realistic 3D example, we can see that there is a mixture of 3D geometries and 2D entities. If we launch Optimize, we are presented with the mode on top. We have been using in the last example the 3D mode, but we can also switch to 2D, and then all the 2D entities in the 3D drawing will be selected for optimization. We will go back to 3D mode for this example, and we will also turn off the 2D lines. We set the distance tolerance to, for instance, 50 millimeters, and press preview. We can see that everything is being optimized. But here on the left, we also want to align these two faces. In order to do this, we will increase the distance tolerance to 200 millimeters. Press preview again. We can see that the distance between these two faces has been closed. But we can also see that all these gaps between all the geometries are being closed, which is not what we want. So again, like in the last example, we will do this in 2 steps. Put it back to 50 millimeters, press OK. We have a first optimization step, then launch Optimize again. But now we will select the entities in the drawing that we want to include for optimization. So we want these 2 geometries. Press Enter. And increase the distance tolerance to 200 millimeters. And you can press OK if you are happy with the result. Moving on to the next drawing optimization tool, Overkill is present to remove duplicate entities. This is a tool that exists already for quite some time, and the goal of the command is to analyze a drawing and to find, for instance, overlapping lines. Since we like the idea of the command, we have extended the functionality with a new mode to also automatically look for duplicate block definitions. If we go to the Drawing Explorer and go to Blocks, we can see that this drawing contains 142 block definitions. But for instance, if we go to the windows, we can see that there is actually a lot of duplication in these block definitions. Launching Overkill, we are presented with a new command option to combine duplicate block definitions. We apply this option, we are presented with a new dialog which also contains the option to purge duplicate blocks. And what this command option will do is it will look for block definitions in the database containing identical geometry. When found, all block definitions in the drawing will be re-referenced to a single block definition. And if we enable this option, these block definitions that are no longer be used will be purged as well. So if we hit apply and look at what the command did, we can see that it found a lot of block definitions that are purged and that were duplicated. For instance, here in the windows, we found a lot of block definitions that are being purged. Now, if we go back to the Drawing Explorer, we can see that now the drawing only contains 53 block definitions. Also, the drawing looks exactly the same, but now we have less block definitions and there is no duplicate information in this drawing. As a next improvement to the drawing optimization tools, we have added a new mode to the Blockify command. Blockify detects similar geometry and replaces it with blocks in order to decrease the file size and optimize DWG structure. When looking at the structure browser, we can see that this drawing consists of 19 3D solids. When launching the Blockify command, we are prompted with the select source entities or match equals solids. What this option does is it will look at all the 3D solids separately, split them in groups of equal solids, and replace all solids with block references to a single block definition per group. If we launch this on the entire drawing, we can see that now Blockify has inserted 19 block references. We can also specify an input set to the Blockify command. For instance, here we can select this small cube and this slightly larger cube. What Blockify will do is it will find all the instances of this pair and it will insert a block for it. Here it has inserted 4 times block 3. We will undo this because we have added a new mode to the Blockify command, which is called find collections. What this will do is it will find all the collections of the blocks inside the drawing. We are shown a command panel, which is similar to the optimize command panel, and it will remain alive during the entire lifetime of the command. Here you can see that we have 5 collections, and we can, for instance, take this collection as before, and we can see that now all the instances of this collection are being highlighted. We can also go over them by using this show option. We will call this small block, and we will create it. Now Blockify will relaunch and calculate all the new possible collections. Here you can see that the small block is also inserted in the collections. We can make a pair of this small block and call it larger block. Now, as a final one, we see that there's only one collection left, but there's a warning: some collections overlap with others. We can highlight it and see that here is the problem. We can show all the instances and see that in instance 2 and 1 there's a problem, so we can remove, for instance, instance 2 from the list, and now we can create largest block. Blockify will exit because there are no collections to be found anymore. And if we launch the structure browser, we can see that there are now 7 block references, including the larger, largest, and small block. Let's look at the power of this find collections feature on a more realistic use case, for instance, from the mechanical context. The structure browser tells us that this drawing consists of 104 solids, and we will first transform them into blocks with Blockify. And now we have 104 block references. Again, we can run the find collections on this, and we are presented with 3 collections. One collection is of the complete piston. The next one is of the base, and another one is of the arm. So let's first start with the base and create a block for that. Let's call it base. Now again, the algorithm shows us that there are 2 collections. One is of the arm, so we will call this the arm. As the last one, this is the complete piston for the smaller. The larger one cannot be matched. So let's call this complete piston. Great. Now if you look back at the structure browser, we can see that we now have actually 5 block references, 1 arm of the larger piston, 1 base of the larger piston, and then 3 complete pistons. This technology can not only be used for 3D, but also for 2D. We will go back to the floor plan from earlier in this breakout session. And we know that this floor plan consists of a lot of block references, so we will just directly launch Blockify with defined collections. We see that there are a lot of collections being found, and some of them make more sense than others. For instance, here we have a pair of tables or desks, but we actually wanted to include the chairs as well. And for this, we will first measure the distance between the chair and the table, which is around 21, and relaunch the Blockify command with defined collections, select the entire drawing, and we will fill in here a gap that is larger than 21 to be sure, for instance 30. We calculate it, and now it finds the desk island with chairs, and here the desk with 3 chairs. So let's first create a block for this desk island, create. We will also create a block for this collection. Let's call it desk with chairs, create. Now we will exit the command, and to show you the power, we will find the similar blocks. You can see here that all 3 of them are selected and are block references. To wrap up, this Find Collections tool is brand new for V22. We're actually really excited about it and are really looking forward to evolving it further in future releases. We'd love you to give it a try and share your experience with us if you have any suggestions for improvements. As the last part of this demo, I would like to talk about applications where surveys, for example, lead to a large amount of data in the format of points. This drawing is actually a part of a scan of a cathedral where the result is a set of points. If you look at the structure browser, we can see that this drawing contains more than 10,000 points, and in order to effectively manipulate this dataset, we additionally would like to have some meaningful geometry. The idea is that you could replace and/or fit lines, arcs, and polylines in this data. For that, we implemented a new set of commands and tools to assist you in this otherwise very tedious process. The first of these tools is the fit line. We are presented with a floating command dialog with a few options, and we can select the points we want to include in the fit. Here we have a preview of the best fitted line, and if we press fit line, the line will be inserted, and you can see here that it is a line. The next one of these commands is the fit arc. You have again a similar floating dialog, and we can select these points of this circle here, and the best fitted circle will be inserted in the drawing. If you go to another example for the arc, for instance, we launch the command again, and here we can see we have a maximum angle gap. What this means is that if the maximum angle distance between 2 points or entities is less than this number, like for instance here 60 degrees, the arc will be closed like we had in the previous example, but here this will not be the case, and the arc will not be closed and will be just an open arc. The last of these fitting tools is very meaningful if you have a complex shape and you want to create a continuous polyline consisting of lines and arcs. For this, we have created the Fit Polyline tool, which we will demonstrate on this point cloud. First, we launch the command and we select the section and the point cloud. Automatically crops the point cloud, and it also generates a guideline, as you can see here, which is the result of an algorithm, and it will help you in creating the polyline. First, we click to make the start point, and then you can see we have 3 control switch options: lines, arcs, and best fits. Best fit will automatically choose between a line and arc, which is at that point the best fit. Such we can start clicking to create the segments, and it will automatically choose a line or an arc. Sometimes it is difficult to create the best fit, and then you can force the algorithm to create a line or an arc by using the control switch. Say from this point you don't want all of these details, so you can just continue placing an arc. Here we want a line. Now these details we do want, so we let it automatically choose. You can see with a few clicks you are generating this complex polyline and making it automatically choose between the lines and the arcs. And it's being fit to the point cloud. Let's say from this point we don't want these details again, so we will draw a line till here, then this arc. Here we will stop because the drawing is symmetrical. We go to the structure browser and isolate this polyline. We can see that we have created a very complex polyline with just a few clicks, which would have been a very tedious process if you would have to create this by hand by using the normal Polyline tool. This concludes my demo for drawing optimizations. I hope it is clear that BricsCAD continues to work on these tools because we really believe that the CAD program can assist the user to organize the data in the most optimal form. Thank you for your attention.